In today's increasingly chaotic media environment, where legitimate journalism must constantly compete with waves of chatbot hallucinations, fabricated claims, and a rapidly spreading epidemic of digital disinformation, it should be obvious that not everything we read can be taken at face value. Yet, despite this awareness, people often find themselves captivated by sensational statements, especially when they touch on grand and mysterious topics like the nature of the universe. Scientific literacy has become more critical than ever, because even ideas that appear in reputable publications can be misunderstood, exaggerated, or taken out of context. This caution becomes especially important when confronting sweeping claims about the cosmos, a subject that already pushes the limits of human understanding. One recent example comes from a provocative study suggesting that our entire universe might exist inside a gigantic black hole. While such a proposition naturally catches the imagination and would indeed have earth-shaking implications if true, it must be approached with careful skepticism, methodical reasoning, and an appreciation for how scientific evidence is built. The study in question was written by Lior Shamir, a computer scientist at Kansas State University, and published in March in the monthly notices of the Royal Astronomical Society. This journal, with nearly 2 centuries of scholarly heritage, is widely respected within the astrophysics community, meaning the work was vetted before publication. On a surface level, the paper seems to present a compelling and visually intuitive finding. Shamir analyzed a dataset of galaxies observed by the James Webb Space Telescope JWST, one of the most advanced scientific instruments ever built. JWST can capture faint and distant galaxies formed billions of years ago, giving researchers a window into the early universe. When Shamir examined the rotational directions of these galaxies, specifically whether they appear to spin clockwise or counterclockwise, he discovered something unusual. Approximately 2/3 of the galaxies in his sample seemed to rotate clockwise, matching the rotational direction of our own Milky Way, while the remaining 1/3 rotated counterclockwise. This uneven distribution is puzzling because, according to a foundational principle of cosmology known as the cosmological principle, the universe should appear roughly the same in every direction when viewed on a sufficiently large scale. That means that the orientation, distribution, and rotation of galaxies should not show a preferred direction. Over vast cosmic distances, no region should be inherently special. If the universe has no built-in directionality, then statistically we should observe about a 50-50 split between clockwise and counterclockwise spinning galaxies in any large, randomly selected sample. Shamir, however, reports a significant imbalance. To him, this is not a simple quirk of random distribution, but may hint at something profound. The universe itself could be spinning. If the cosmos as a whole were rotating, that rotation might cascade through all cosmic structures, subtly influencing how galaxies form and orient themselves. Among the explanations Shamir offers for a rotating universe, one stands out for its boldness: the idea that our universe exists inside a massive, rotating black hole. In general relativity, many black holes, especially the type known as Kerr black holes, rotate. If our universe were somehow nested within one, that rotation might imprint itself on everything inside, including the galaxies surveyed by JWST. This speculation, while dramatic, is not without historical precedent. Over the past century, physicists and cosmologists have occasionally explored the possibility that black holes and universes may be intimately connected. Some theories even propose that new universes could form inside black holes, with the singularity acting like a cosmic seed. But these ideas remain speculative and difficult to test. Cosmologists would undoubtedly be thrilled if evidence emerged showing either that the universe rotates or that it is the interior of an enormous black hole. Such discoveries would not only rewrite physics textbooks, but also open the door to entirely new fields of research. They might help solve persistent mysteries, such as the nature of dark energy, the cause of cosmic acceleration, or the Hubble tension, a puzzling mismatch between different measurements of the universe's expansion rate. A rotating universe might also introduce subtle effects that could be observed with precise instruments, offering new clues about the structure of space-time itself. Beyond the academic excitement, the idea is undeniably fascinating. Most people would find it entertaining, even thrilling, to contemplate over dinner or bring up in conversation during a date night. It stretches the imagination and reminds us of how small we are relative to the cosmic vastness. However, before embracing such revolutionary conclusions, scientists must investigate alternative explanations and examine the data carefully. Astronomers have long considered the possibility of a rotating universe. One of the earliest and most famous examples comes from 1949, when Kurt Gödel, an influential mathematician and close friend of Albert Einstein, developed the solution to Einstein's field equations that described a universe with global rotation. Gödel's rotating cosmology had striking implications. It allowed the theoretical possibility of traveling into the past via closed time-like curves. Gödel used this model in part to challenge Einstein, suggesting that relativity might permit time travel, a feature Einstein found unsettling. Although Gödel's universe is mathematically valid, it is considered physically unrealistic because there is no observational evidence that our universe rotates in the way his solution describes. The fact that scientists have explored these concepts for nearly a century illustrates both the creativity and caution required in theoretical cosmology. Theories about the early universe, black hole interiors, and the behavior of space-time often involve extreme conditions that cannot be replicated in laboratories. Instead, researchers rely on indirect evidence, mathematical models, and astronomical observations. Any claim that challenges the cosmological principle, such as the notion of large-scale rotational asymmetry, must be backed by substantial and reproducible data. Observing a disproportion in galaxy rotation directions might seem like such evidence, but scientists must consider whether the sample size is large enough, whether there are observational biases in the data, and whether alternative interpretations are more plausible. One possible concern is that determining a galaxy's rotation direction from telescope images is not always straightforward. Depending on the viewing angle and the galaxy's orientation relative to Earth, it can be difficult to confidently identify which side is rotating toward us and which is rotating away. Dust, gas, bright star clusters, and gravitational distortions can also obscure the structure. Automated algorithms, though powerful, may misclassify rotation directions, particularly in faint or distant galaxies. Additionally, the area of the sky surveyed by JWST might not be fully random. Certain regions could contain clusters or filaments that naturally produce uneven distributions due to local cosmic structure. If the galaxies in Shamir sample are not spread uniformly throughout the sky, the imbalance could result from local cosmic variations rather than evidence of universal rotation. Another consideration is cosmic variance, the idea that the universe may show fluctuations or irregularities in smaller regions, even if it is uniform on the largest scales. For instance, some areas of the universe contain more galaxy clusters or dark matter than others. These natural variations can distort statistical results, especially when dealing with samples that are smaller than the total observable universe. It is therefore crucial for researchers to analyze multiple independent datasets, use different telescopes, and compare results across various wavelengths before drawing global conclusions. Scientists also emphasize the importance of peer review, replication, and open scientific debate. A single paper, no matter how intriguing, cannot overturn established principles without consistent support from broader evidence. The idea that the universe is spinning or located inside a black hole is not dismissed outright. Rather, it is held to strict scrutiny, as is the case with any extraordinary claim. The scientific method thrives on questioning assumptions, but it also demands rigor before accepting new frameworks. Particularly in cosmology, where observational limitations are significant, theories must align with everything else we know about gravitational behavior, cosmic microwave background radiation, galaxy formation, and the large-scale distribution of matter. In this era of instant information, rapid sharing, and the viral spread of sensational stories, it is more important than ever to slow down and examine scientific claims thoughtfully. The allure of dramatic explanations, such as living within a colossal spinning black hole, can overshadow the careful, patient work of science. But true understanding comes not from the boldness of an idea alone, but from how well it withstands repeated testing, observational consistency, and theoretical coherence. The universe remains full of mysteries, and new discoveries will continue to challenge our understanding. But until we have overwhelming multi-layered evidence supporting such extraordinary propositions, caution remains our most reliable guide.